Okay, this is AP, AB, and BC Calculus. We're doing Unit 3, Section 2, which is implicit differentiation. So what you've been doing so far is called explicit differentiation. We haven't discussed that, but basically that's just what you naturally do already when your equation is solved for y. Since most of our equations are solved for y most of the time, it hasn't been a big deal. When you cannot or should not solve for y, you use implicit differentiation, which is basically just applying the chain rule. So I'm going to explain to you context about what I mean by should not solve for y and also cannot solve for y as we move forward. So when I say should not, it means that there are other ways to do this problem, but that implicit differentiation would by far be the easiest. So when you differentiate y stuff, you have to apply the chain rule and differentiate the y itself, usually with respect to x, so that would be dy dx, although later in the course we'll differentiate with respect to other variables, often t for time, and when we get to BC topics, sometimes we'll differentiate with respect to theta, which is an angle, right? So, for example, if I asked you to differentiate, that's what dy dx means, the quantity y squared plus 3x to the fourth, then when you differentiate the y squared, right, the derivative of stuff squared is 2 stuff to the first, hence 2y to the first, and then I would multiply by the derivative of the y itself, which would be dy dx. And then when I differentiate the 3x to the fourth, since I'm differentiating with respect to x, and x is the variable, the derivative would be 4x to the third, and then technically, if it helps you, your brain can actually think, oh hey, I differentiated x with respect to x, which is actually not false, but that's 1, so we never read it. So it's not actually like you're not differentiating with respect to x, like x with respect to x, it's just that dx is 1 anyway because it's something over itself, so we never read it. So you've actually been doing this naturally the whole time. If you think about what you would have done if I gave you an equation like y equals 7x to the fifth plus 6x, when you differentiate, you would have written this side as either a dy dx or a y prime. That's it. That's what we'd use. That's the notation we use for derivative. And then on this side, you would have gotten the 35x to the fourth and the plus 6. So you're naturally doing this already because when y is by itself and you differentiate, you know to write dy dx or y prime, right? So you either write y prime or dy dx, right? So I'll write or y prime, right? Okay, so moving forward, let's go ahead and walk through an example. So we're going to find dy dx here. So it's all sums and differences, so I'm just going to differentiate each individual piece. The derivative of stuff to the fifth is 5 stuff to the fourth, but because the stuff wasn't an x, I need a dy dx when I differentiate. Plus, the derivative of cosine of stuff is negative sine of the stuff, and since that stuff wasn't just an x, I have to use the chain rule and multiply by 2. Equals, now when I differentiate tangent y, well, the derivative of tangent of something is secant squared of that something. But because that something wasn't an x, I need to make sure that I differentiate the thing with respect to x, plus, and then when I differentiate the 3x squared, I'm going to get a 6x, right? So now I want dy dx. What that means, if I'm asked to find dy dx, sorry for the beach balling, this means solve for dy dx. So what I need to do is I need to move all my dy dx's to one side. I'm going to do that by subtracting the secant squared y dy dx over, and by moving over the sine quantity. So what's going to happen is I'm going to get 5y to the fourth dy dx minus a secant squared y dy dx. So what I did is I moved all of my dy dx's to the left-hand side. And then I'm going to go ahead and add this sign over to the other side. So all my non-dy dx's are going to go to the right-hand side. So over here, I seem to have a 6x, and then when I add this over, I get a plus 2 sine of 2x, right? Then I'm going to go ahead and factor out this dy dx, right? This dy dx is actually a common factor that I can yank out. So I'm going to factor that out, right? It is a common factor. In this case, it is actually also the greatest common factor. Sometimes it won't be the greatest common factor, sometimes it's just a factor. What's left when I factor that out is a 5y to the fourth minus a secant squared of y. And on the other side, I still have this 6x plus 2 sine of 2x. And now to get dy dx by itself, I'm just going to divide this over. So I'm going to get dy dx is equal to 6x plus 2 sine of 2x over 5y to the fourth minus secant squared y. And that's a 5. It kind of came out like a 6, but it's a 5. And there's my dy dx, right? So I solved for dy dx. Now, if you had gone the other direction, see how I moved all my dy dx to the left-hand side? Another option is if you went the other direction, you would get exactly the opposite signs. So if you got exactly the opposite signs, that just means you went the opposite direction of what I did. So you got a negative 6x minus a 2 sine of 2x on the bottom. You got a negative 5y to the fourth and a positive secant squared y, or some version of putting that in a different order. But again, if every single sign is opposite, it's the same answer, because you could factor out a negative 1 from the top and bottom and cancel them, and you would have gotten my answer. So just be aware that your answer might not always match a multiple choice answer, but you then need to take a deep breath and look at your answer and see if you can figure out which one is actually yours. All right, so you're going to go ahead and try one. It's similar. You can pause me if you want to do this on your own without me, and I'm going to go ahead and walk through. So we're finding dy dx. So 3y squared dy dx, because I just differentiated some y stuff, right, plus e to the 4x times the derivative of the inside, which would be a 4, equals the derivative of sine of y is cosine of y times that dy dx, because I just differentiated y stuff, right, plus a 15x squared. I like my dy dx's on the left-hand side, so I'm going to move them this way, and I'm going to move the e stuff this way. So I'm going to end up with a 3y squared dy dx minus a cosine y dy dx equals a 15x squared times this, minus this 4e to the 4x. So, because I subtracted that over, right? So, and then I'm going to factor out my dy dx, right? And when I do that, I'm going to be left with everything that wasn't a dy dx on this side, which is the thing I'm going to divide by and make my denominator. So my final answer is going to be dy dx equals 15x squared minus 4e to the 4x all over 3y squared minus a cosine y. Now, it's worth noting again that if all the signs were exactly the opposite, it would be the same correct answer, right? So if you had gone the other direction, your answer might have looked like this. Your answer might have been something like dy dx equals, chances are you tend to put positive things in front, so you might have just literally switched the order, and if the e to the 4x is positive, most of us sort of naturally put that in front, and the same thing's true with the cosine of y. So that's also the same answer, right? Same idea. Again, you don't have to have the exact same answer I have, but you have to be able to spot if your answer is the same. A common AP trick is to have an answer that looks just like your answer, but with a single sign that is wrong. For instance, to have this be a plus cosine y on the bottom, and that would be a wrong answer. If all of the signs are the opposite, then it's the same answer that you have. But if only one sign is different, then be careful, because it's probably a trick. All right, so in example 2, we're going to have a product rule. So when I introduced the product rule to you, I told you that it was generally two functions of x that were a product that could not be simplified. And that's a sort of general rule for when you're only dealing with functions of x. But the larger rule is that it's any two functions that are multiplied and can't be simplified into one function. So I do have a product rule on the left-hand side, and then the right-hand side is just a sum or difference, so that won't be awful. So on my left-hand side, I'm going to have u dv. Well, the derivative of v is going to be 4 stuff cubed, and the stuff is a y in this case, times the derivative of the stuff. So notice that I just differentiated y stuff, so I have a dy dx, plus v, which is the y to the fourth exactly as it is, du, which is going to end up being an 18x squared. There's no dy dx because I didn't differentiate any y stuff. I differentiated the 6x cubed. On the other side, that's going to equal the derivative of 8x, which is just an 8, and the derivative of 3y squared, which will be a 6y to the first, times dy dx, because I'm differentiating y stuff. And then we're going to follow the same basic set of rules that we've been using, which is we're going to move our dy dx's to one side. You'll notice that I almost always default to moving my dy dx's to the left. The only reason I could see that I wouldn't is if almost all of them were already on the right and I just had to move one over. So I'm going to get 6x squared y, 4y cubed dy dx minus this 6y dy dx equals an 8, and then when I subtract over, I'm going to subtract the 18x squared y to the fourth. If you want to go ahead and clean this up ahead of time, you can. So I'm going to end up getting that this is, when I factor my dy dx out on the left-hand side, I'm going to get a 24x squared y cubed minus a 6y. And you'll notice that the dy dx isn't the GCF in this one. I could have also taken out a 6 and a y. But here, really, our goal is to solve for dy dx, so we don't have to do a bunch of other stuff. And on the other side, I get an 8 minus an 18x to the 4, or x to the second, y to the fourth. Then I'm going to go ahead and divide by this stuff in the parentheses, and it'll become my denominator. So I'm going to get dy dx equals 8 minus 18x squared y to the fourth on the top. And in my denominator, I'm going to get a 24x squared y cubed minus 6y. Right? And if you got an answer where every single sign was the opposite, it would be the same answer. If you got an answer that factored out a 2 from the top and a 6 from the bottom, or canceled some of those things, that would also be fine, because you'll notice that you could factor out a 2 from the top, you could factor out a 6y from the bottom. So any number of other answers would be the same basic idea. Okay, let's go ahead and go to AP2. All right, so same idea. This time you're going to have a quotient rule, right? You have a high, you have a low, and there's not anything you can do about that. So when you differentiate your left-hand side, you're going to have low. D high is going to be a 15x squared minus high, which will be a 5x cubed. D low, well, now I'm differentiating y stuff, so that's going to be a 2y dy dx, right? I'm going to draw the line, and I'm going to square the low, which is going to be a y squared squared, or y to the fourth. Notice I didn't differentiate the y on the bottom, it's just low squared. On the other side, the derivative of cosine of 3x should be negative sine of 3x times the 3 for the chain rule, right? So the 3 is not inside the sine, right? And then when I differentiate sine of 2y, I should get cosine of 2y times the derivative of 2y, which would be a 2 dy dx. Again, notice that the 2 is not inside the cosine. So I'm going to suggest that the easiest way to simplify this is to multiply this y to the fourth over, because nobody wants a fraction inside other fractions. It's just kind of ugly. So I'm going to go ahead and multiply this y to the fourth over. I'm going to get y, let's clean it up as we go, actually, because we're sort of tight on space, and it's going to be a lot easier if we clean up as we go. So on top here, this is a 15x squared y, so I'm going to go ahead and write that as a 15x squared y squared, my bad. Minus the 5 and the 2 would give me a 10x cubed y dy dx, right? When I multiply the y to the fourth over on the other side, over here, I'm going to get a negative 3 y to the fourth sine of 3x, and plus a 2 y to the fourth cosine of 2y with a dy dx. And now I'm pretty much in the same spot I've been. This entire term needs to go to the left-hand side, right? And then this entire term needs to go to the right-hand side. Again, you don't have to move all your dy dx's to the left. I just generally default to doing that. It's certainly up to you. So when I do that, I'm going to get a negative 10x cubed y dy dx minus a 2y to the fourth cosine of 2y dy dx. And on the other side, with no dy dx's, is going to be a negative 3y to the fourth sine of 3x minus a 15x squared y squared. Right? I'm going to factor out my dy dx. And if you can do this in your head without actually writing the extra step, when I factor that out, this is the thing I'm going to be dividing by, right? So my dy dx is going to be a negative 3y to the fourth sine of 3x minus 15x squared y squared, all over the negative 10x cubed y minus a 2y to the fourth cosine of 2y. You'll notice all of those signs came out negative, so it's very possible in this case that people would have moved stuff to the other side and would have had this be the exact same answer, but with all the signs being positive. That's a sine of 3x, sorry, it's a little crammed, plus 15x squared y squared over a 10x cubed y plus a 2y to the fourth cosine of 2y. Same answer, right? And there's not much you can do. There are some GCFs that you can factor if you wanted. I don't know that it really benefits you. You could yank out a y from the top and bottom and cancel it. But again, I don't know if it really benefits you that much. So again, if you don't need this step where you write this, it's okay to skip steps, right? What you shouldn't do is you shouldn't skip from here to the answer. That's too many steps to skip. You're expected to demonstrate knowledge along the way. And even if you could do it in your head, which is quite possible, you shouldn't. You should make sure you show some steps along the way. All right. Cool. Let's go ahead and do an E3. So here we can solve for y, but it might well be easier to differentiate implicitly. Let's walk through both options, okay? So we're going to find dy dx two different ways, right? So option one, we're going to solve for y. And I'm going to argue that this is not the better option, because remember, I told you that sometimes you can solve for y, but it's not a great plan. So you're going to get y squared equals 25 minus x squared, right? So you're going to get that y is equal to plus or minus the square root of 25 minus x squared. Or if you want, you can write this as a plus or minus a 25 minus x squared all to the 1/2. Cool. So now when you differentiate to find dy dx, you've got a chain rule, right? And there's a plus or minus in front. You can just leave it with that plus or minus, right? So you're going to get a plus or minus 1/2 25 minus x squared to the negative 1/2 times a negative 2x, right? Because that would be the derivative of the inside, right? So you could keep it as a plus or minus, because even with the negative, I mean, technically it becomes a minus or plus, but it doesn't really matter. So you're going to get a plus or minus. The 2's would cancel, and you're going to get an x on top of this square root. And that's fine. There's nothing wrong with it. It's great. Okay, so that's one option. But I think a lot of us are going to get thrown by the plus and minus. I think a lot of us aren't going to have a great time dealing with the square root. There's a lot of stuff there to unpack. The other option is to not solve for y, and we're going to see that we get the same answer. So we're going to try it implicitly. So x squared plus y squared equals 25. Now let's differentiate. So 2x, technically dx dx, but nobody writes it, right? Plus 2y to the first dy dx equals 0, right? So I'm going to go ahead and solve for dy dx. Now this might be a really good case where it's worth putting your dy dx on the other side, because if you notice, dy dx is you know, there's not really a huge incentive, but if you want, you could put it to the other side. I'm going to keep it on my left-hand side. Since there's only the one dy dx, doesn't really matter. I'm going to divide by the 2y, and I'm going to get the dy dx equals essentially a negative x on top of y. And you might say, okay, cool, that's great. That looks a lot better, but how is it the same answer? Well, if you look at what we said y was, right? We said that y was plus or minus this square root. So in fact, if we go back a second, if I don't cancel the way that I did originally, you could have left this as a negative x with the plus or minus. Again, I promise you that it's the same. You could either write it as a negative x with plus or minus, or you could write it as a negative x or you could get rid of the negative and call it a minus over a plus. It doesn't really matter. But sure enough, here's my y, right? Because this whole thing, the plus or minus the root, right? There's my y, because we just saw that. And then the negative x, there's my negative x. So I think it's a lot easier to do this implicitly, but again, you can solve this for y. I just don't think it's worth it. So I'm going to give you another one where you can, if you want, solve for y. I just don't think it's a great option. So again, we're going to find dy dx, and you can use either option. I'm actually going to start with the implicit option first here. Okay, so if I did this implicitly, when I differentiate, I'm going to get a 4x, right, to the first, plus a 3y squared dy dx equals a 0, right? Because I differentiate the 6 and I get a 0. I move the 4x over, I get 3y squared dy dx equals negative 4x. So my dy dx is a negative 4x over a 3y to the second. I never had to do anything other than use pretty straightforward power rules, and it turned out pretty nice. Nothing wrong with that. Okay, so let's say you chose to do it the other way, right? So the other option is that you solve for y, and there's nothing wrong with it. It's just going to give you a different option. So if I do that first, I'm going to get a y cubed equals a negative 2x squared plus 6. And then I'm going to cube root both sides. So I'm going to get y is, now you don't need a plus or minus when you write a cube root. And I'm going to write that cube root as a 1/3 power because I know I have to differentiate. So then my dy dx is going to be 1/3 negative 2x squared plus 6 to the negative 2/3, right? Because I dropped the power by 1. Times the derivative of the inside, which is going to be a negative 4x, right? So if I clean that up a little, that seems to be a negative 4x on the top over a 3, and then what I have here is a negative 2x squared plus 6 to the 2/3, right? Well, if you look at what y is, right? Y is this thing to the 1/3, right? Well, this is the same as saying negative 4x over 3 negative 2x squared plus 6 to the 1/3 quantity squared. That's the same thing as saying a y squared. These are the same answer, and one of them came out a lot easier. I think the one in blue is a much easier answer. Again, either of them is going to get you to the same place, but it's a lot easier to do this implicitly, in my opinion. All right, let's go ahead and do an E4. So we're going to go back to our classic tangent and normal line question that we've seen in almost every video, right? It's a good application. So we're going to write the equations of the tangent and normal line to the curve. So remember that anytime you hear the equations of lines, right, we know we need two things. We need a point, which we've already been given half of. And the reason I start with this is because it's not a calculus skill, it's an algebra skill. So the trick here is that since I'm not solved for y, I'm going to have to plug in and solve. So I'm going to get 2 times a negative 1 squared, which would be 1, plus y cubed equals 10. So y cubed seems to be an 8. Looks to me like my y is a 2. So I now have the point 1 comma 2. Great. First half done, no calculus involved, just pre-calc, right? Second thing I need is a slope, right? So I know that my tangent slope for A is going to be whatever the derivative is evaluated at that point negative 1 comma 2, right? And I know that my slope for B is going to be the opposite reciprocal of what I got for A. So there's no skipping to the second thing. You got to do the work to find the tangent slope first. So I'm going to go ahead and find dy dx. Based on what we saw in E3 and P3, I'm going to suggest that you do this implicitly. It's going to make your life a lot easier. So I'm going to get a 4x to the first plus 3y squared equals 0, right? Oh, sorry, I forgot my dy dx. Come on, people. My brain, tragic. Look at me not doing the right thing. Come on, brain. All right. Sometimes there's not enough coffee, people. Don't judge too hard. So when I solve, I'm going to end up getting that my dy dx equals a negative 4x over a 3y squared, which is actually the same one that we saw in a previous example. So my tangent slope is going to be dy dx, and remember the way that we write that we're evaluating at an x value or at a point is we use this vertical line. So dy dx evaluated at negative 1 comma 2. Well, that's cool because all I have to do is plug in a negative 1 for x and a 2 for y, right? So I'm pretty sure I get 4 over 12 or 1/3, right? So now that I know that, I also am able to find my normal slope, right? My normal slope should be a negative 3 over 1 or just a negative 3. So then that's enough with my point and my two slopes to answer my questions, right? Y minus the y value equals my tangent slope, which was the 1/3 x minus the x value. If you really want to add the 2 over so that it's solved for y, you absolutely can, right? And for b, I write this exact same equation, but instead of the 1/3, I'm going to put a negative 3. So I can either write it this way, y minus 2 equals negative 3 times the quantity x plus 1, or I could write it as y equals negative 3 times the quantity x plus 1 plus a 2. Either of those are fine. So I think you'll see a lot of times the AP does this where they solve for y, but they don't bother to distribute. But certainly any of those answers would have been fine. All right, let's do a P4, and that'll be it for this video. Same idea. Tangent and normal lines, you're given an x value. So first thing you need is a point, right? That's not a calculus part of the question. That's just saying in order to find the equation of a line, you need a point, 2 comma blank. To find that blank, I'm going to plug in x is 2. So that's going to be 5 times 4 plus 3y to the 5th equals 17, right? So I get, I think, 3y to the 5th equals negative 3. Y to the 5th is a negative 1. So if a power of, if I do y to the 5th and I get a negative 1, then y must be a negative 1, right? Negative 1 times itself 5 times gives me negative 1. So essentially what that is it's a 5th root of negative 1, but mostly we can use logic to figure out that that's a negative 1. Second thing I'm going to need is a slope, right? My tangent slope should be whatever my dy dx is evaluated at that point 2 comma negative 1, right? That's my tangent slope. And my normal slope is going to be the opposite reciprocal of the tangent slope, right? So again, I have to find the tangent slope first, and then let's say you completely mess up finding the tangent slope, which is a bummer, but let's say you do. Make sure for part B, you still use the opposite reciprocal of the slope you found in A. Even if you know A is totally wrong, you should still use the opposite reciprocal to show that you understand that that's what normal means. So let's go ahead and differentiate. Again, much easier to do this implicitly. So 5x squared becomes a 10x plus, this will be a 15y to the 4th dy dx, and then when I differentiate the 17, I get a 0. So I'm going to subtract the 10x over and divide by the 15y to the 4th. So I'm going to get the dy dx is a negative 10x over a 15y to the 4th. Now you could leave it like that. Remember that at this point in math, you're simplifying selfishly. I'm not going to leave it like this because I don't feel like dealing with numbers that are multiplied by 10 and 15. That's just not a thing I want to deal with. So I'm going to go ahead and cancel a 5. You don't have to, but I'm going to argue that it's a lot easier if these numbers are smaller, right? So that's a choice. It's fine to use this. So that means that my tangent slope is going to be dy dx, and you do want to use this notation. You want to get comfortable using this notation. Evaluate it at 2 comma negative 1. So that's going to be negative 2 times 2 over a 3 times what will come out as a positive 1. So I get a negative 4/3. Once I know that, I know my normal slope must be a positive 3/4, right? Opposite reciprocal. And now I can answer both of the questions. So A, my tangent line is y minus the y value, so that'd be plus 1, equals m, which was negative 4/3 times the quantity x minus 2. If you want to solve for y, just subtract the 1 over. Don't bother to distribute, right? The more math you do, the more likely you are to make a silly mistake. For B, if I just want to skip to the end, it's exactly the same answer, but with the slope of 3/4 instead, right? And there you go. All right, that's it for Unit 3, Section 2.